Welcome back to Chem 4300. In this video, we're going to begin Chapter 7, which looks at the electrostatic interactions of atoms and molecules. Now, in the previous chapters, we've been looking at the various types of motion that atoms and molecules can undergo, right? So we saw things like translational motion, rotational motion, and vibrational motion. Now, in all of the discussion of the physics describing those motions, we didn't really talk at all about the forces that cause those motions. Now, we know at the atomic level that gravitational forces are not going to be significant, right? They're going to have a very negligible effect on atoms and molecules. And what we're going to learn in this chapter is that the origin of those forces is primarily electromagnetic in nature. So what we're going to be going after are questions like, what is the force that acts on a molecule in an electric field? So for example, you know that if there was a molecule that was a cation or an anion and it was in an electric field, it would start to translate in that field. Similarly, if it had an electric dipole moment, you'll see that in that field there might be some torque that's applied that will cause the molecule to rotate. Similarly, if it was in an electric field, we might imagine the electric field might cause the molecule to stretch, and that would start causing vibrational motion to occur. So we're going to be looking at the types of forces that will be generated on a molecule when it's in an electric field. We're also going to be interested in the attractive and repulsive forces that are going to be acting between molecules that are going to be, again, electromagnetic in nature. So we're going to be exploring how this molecule will generate electric field over here, and this one similarly will generate one over here, and that will cause some interaction between the two guys that will lead to some repulsion or attractive force. Now, I think it's really important to understand that electrostatic interactions are at the heart of a lot of chemistry. So understanding electrostatic interactions is important if you want to understand, for example, why gas molecules will condense into the liquid phase. That attraction there is electrostatic in nature, which will bring gas molecules into the liquid phase, similarly bring them into the solid phase. It's also important for understanding the origins of friction and how you might improve the situation in lubrication. It's also important in concepts of adhesion and wetting phenomena. You're going to see that that plays a critical role in molecular self-assembly, for how biological membranes assemble themselves, even protein folding, and life itself is really dependent upon these electrostatic interactions to function the way it does. So this is what we're going to be looking at in this chapter, and we're going to start by just going back to a review of our basic high school or sophomore physics here. So we'll start with Coulomb's law. If you remember that a collection of charges will exert a force on some test charge, and we were able to describe that force on this charge here as the sum of each individual force on this test charge. And so that expression, which is Coulomb's law, is given here. So the test charge, Q, divided by 4 pi, an electric constant, is here, and then is going to be a summation of each of these individual charges weighted by this quantity involving the positions, relative positions of each charge to the test charge. This quantity here that I've put in blue can be lumped together into a new quantity that's called the electric field. This is what we saw that Faraday was responsible for. And that electric field quantity then is independent of the test charge. It just says that these charges over here will generate, not only here, but any point in space, an electric field vector, which can be calculated using this expression here. Now, in this chapter, we're going to be focusing on atoms and molecules. And even though atoms and molecules consist of nuclei and electrons, which are particles, or at least we're talking about them now as particles, we're going to find it convenient to approximate the atom and molecule as a continuous charge distribution. So instead of discrete charges, we're going to just describe the molecule as a charge density that exists in space in some volume. And we're going to replace this expression for the electric field vector, which has a summation, with an integral expression, which now integrates. Instead of discrete charges, we're going to have the continuous charge density, and we're going to do this integral here to get the electric field vector at any point in space near this charge density, which is going to be our atom or molecule. Now, from this expression, we can also derive something called the electrostatic scalar potential. So just to remind you that the electric field vector can be derived from a quantity called the electrostatic scalar potential by taking the gradient of that scalar field and then the negative of that. So this is analogous to what we learned with forces and potential energy. We learned that the force vector field can be derived at any point in space from the potential energy scalar field. So the scalar field is just a number defined at any point in space, but you can take the derivative with respect to all three directions, calculate a vector quantity called the gradient. The negative of that was the force that would be acting on a particle at that point in space. So here we see the analogous operation that if we have a scalar potential field defined, a scalar number defined at all points in space, we take the derivative along x, y, and z, we construct a vector. The negative of that vector is the electric field vector at that point in space. So this is a very valuable concept, just like conservative forces, which are derived from potential energy, make them easier to work with, some very special properties. The electric field shares some of those kind of behaviors, mathematical behaviors, because it can be derived from an electrostatic scalar potential. So what we're going to do then is we're going to take our expression from the previous page here, where we describe the electric field vector, and now we can describe the electrostatic scalar potential and calculated from the continuous charge distribution. So for a molecule that's sitting in space with some charge distribution, we can calculate the electrostatic potential at any point around that molecule using this expression and doing a volume integral over the volume, over the charge density of the molecule. All right, now let's look at the electric field generated by an atom or a molecule. Okay, so we'll start here. So we're going to take our molecule, some sort of continuous distribution of charge density, positive and negative charges all together, and we're going to calculate the electric field vector at this point in space, or more generally what we're going to do is we're going to calculate the scalar potential at this point in space, and then from that scalar potential we'll calculate the electric field vector there. Now, in this picture, what we're going to do is make an approximation. We're going to assume that we're going to calculate this quantity at a distance that's very far from the molecule. Far in the sense that the distance r here is much larger than the radius of the molecule. So if r is much bigger than the radius of the molecule, then we find that we can do a Taylor series expansion of this part of the scalar potential equation. So if I take this 1 over r minus r prime, these vector quantities difference here, I can do a Taylor series expansion and turn it into this expression. So this is a series expansion about r prime equals 0. Now, I'm not going to expect you to derive this, but you worked with Taylor series expansions before, and so this should probably make sense to you, but you can try to derive it. It's not that difficult. But the important point is that we're going to take this expression, we're going to substitute it in here, and we're going to get a series expansion for the scalar potential at some point out here, and the approximation that r vector is greater than the radius of the molecule. And now the result of that substitution and expansion, and this is all in the notes so you can go back and verify that, but it's not that difficult, is you get this expression here. So here's our series expansion for the electrostatic potential, and it is given in terms of quantities that we are calculating from the charge density. So in this series expansion, the leading term is this term here, which is Q over R, and Q is something that's defined as the electric monopole moment, the charge of the molecule. So if it's a cation, it's a positive value. If it's an anion, it's a negative value. If it's a neutral molecule, this Q will be equal to 0. But this is just simply taking an integral over all the charge density and in the volume of the molecule and getting this quantity Q, which is a scalar quantity, single number, just the charge that is enclosed in the volume of the molecule. And this term is the leading term. It's Q divided by the distance away for contributing to the scalar potential generated by that molecule. Now, if we were, instead of using a charge density, if we were doing a continuous sum over protons and electrons. If we wanted to treat it discretely, then it would be this sum over here. But the general story is the same. There's no need to assume a charge density. It could be a distribution of discrete charges. You can still do this expansion. Now the next term is something called the electric dipole moment vector. So in this derivation, you'll find that you can do an integral of the position vector times the charge density and integrate over the volume, and you end up with a vector quantity. This is called the electric dipole moment. And that is the next leading term, which you can see this is mu dot r over r cubed. So this r up here and r cubed down here. So this whole term goes as 1 over r squared. And so that's going to have a smaller contribution than this guy, because this is 1 over r, which has a bigger effect than 1 over r squared. But of course, if Q is equal to 0, if it's a neutral molecule, then this would be the leading term in determining the scalar potential at some distance away from the molecule. Okay, so that's what's called the electric dipole moment. And the next term in the series is something called an electric quadrupole moment. And this guy is calculated according to this expression here. Now, this quantity is called a second rank symmetric tensor quantity. Now, normally that would seem kind of scary at this point, but we've just had the chapter earlier on rotational motion, and we saw how to calculate the moment of inertia tensor. So we're relatively familiar now with second rank symmetric tensor quantity. So there's the monopole, which is a scalar quantity, or a zero rank tensor if you'd like. Electric dipole moment, which is a vector quantity, or first rank tensor. And the electric quadrupole moment, which is a second rank tensor quantity. And these are all needed in this expansion of the scalar potential at some position away from the molecule. So this is the expression here, and you can calculate that again over the volume of the molecule. So what we've done then is we've used that Taylor series expansion to calculate the potential at some distance away from the molecule, and we've taken this expression from your sophomore physics and converted it into this simpler expression in terms of the charge, the dipole moment, and the quadrupole moment. And if you'd like, you can go on to higher moments. These would be things like an octopole and a hexadecapole, as we'll see in a minute or so. And these moments, which are defined entirely in terms of the charge density and how they're distributed, just like a moment of inertia tensor calculation, for example, you can calculate these guys once and for all for a molecule, and then you can calculate for these, with these moments, the charge at any point away from that molecule with this expression. And of course, once you have the electrostatic potential at any point, you can always calculate the electric field vector at that point too. These are some examples of what kind of configurations would lead to these moments. So of course, a monopole is just simply some charge. It could be a positive charge or a negative charge, doesn't matter, but that would be the configuration you would get. In terms of the electric field, which is the gradient of that guy, then the electric field would go as 1 over r squared. So this guy would go over as 1 over r, but the electric field, which is the gradient, will go as 1 over r squared in terms of its strength as you move away from the molecule. The dipole moment, the configuration that will give you a dipole moment would be this configuration. If you had a negative and positive charge sitting at some distance away from each other, that would be neutral, so it would have no monopole moment, but that would have a leading term, which is a dipole moment. And that guy, the electric field, is going to fall off as 1 over, generated by this guy, is going to fall off as 1 over r cubed. So the scalar potential falls off as 1 over r squared. The electric field, which is the gradient, falls as 1 over r cubed. Similarly, this configuration here, with like two dipoles that have been flipped back to back here, gives you what's called an electric quadrupole moment. So this has no monopole, no dipole. The leading term is the electric quadrupole moment. And this will generate an electric field that falls as 1 over r to the fourth. And if you're curious, there are other moments here. So this would be a configuration that gives you an octopole moment. And I'll let you Google around to find what a hexadecapole moment configuration might look like. But this has no monopole, dipole, or quadrupole moment. This configuration has a leading octopole moment. Now the dipole is something that we're going to be talking a lot about. And so if a molecule has no charge, so if it's a neutral molecule, then the leading term is going to be its dipole moment. And the SI unit for a dipole moment is the Coulomb meter, but that tends to be a number that's on the order of 10 to the minus 30 for most molecules. So we're going to define this quantity here, which is called the Debye unit. That will be more convenient for talking about dipole moments on the atomic and molecular scale. And here are some typical values for moments that you would get for different types of molecules, polar molecules here. And everything you remember about looking at a molecule and deciding whether it's polar or nonpolar from freshman chemistry is still true. We're still going to be using those kind of concepts here in this course, but we're going to be a little more quantitative. But these are the values that you get if you were calculating for or measuring these molecules. Now, one of the things we're going to be talking about is dipoles, and a quantity that, or a model that we're going to be using is something called the physical dipole, which is two equal and opposite charges that are separated by some distance d. So a physical dipole, as opposed to some, say, charge distribution that leads to a dipole, a physical dipole, which has this configuration, has a dipole moment that can be calculated out very simply. These charges have the same magnitude q, but we're going to have so q times the position vector for r minus q times the position vector for q times the position vector for the positive charge minus q times the position vector for the negative charge gives us the dipole moment vector, which works out to be q, the charge on either, the magnitude of the charge on either one of these guys, times the distance vector, which goes from the negative charge to the positive charge. So this is what's called a physical dipole, and we'll use this later in this chapter and the rest of the course. So one of the things that you want to be careful about is, if you're thinking about dipole moments, is that in physics the dipole moment vector is drawn from the negative charge to the positive charge, but for some reason chemistry books tend to draw it from the positive charge to the negative charge. So if you think you got some sign issue, be careful, there might be a different convention. So we're going to be following this convention, that it goes from negative to positive in this text, in this class too. Now, another interesting aspect of multiple moments is that they can depend upon your origin that you choose, which similar to what we saw with the moment of inertia tensors too. So if we look at the different moments, we'll find, though, that the lowest non-vanishing multiple moment is always independent of the origin choice. And then all of the higher multiple moments will depend on the origin choice. So this is a useful little point to remember. So in other words, a monopole is always independent of origin. And so if your lowest non-zero moment is the monopole, then that means that the dipole, quadrupole, octupole, etc. will all depend upon the origin that you choose in doing the calculation that we saw a few slides earlier. Similarly, if the lowest non-zero moment is the dipole, in other words, there's no charge, but the molecule has a dipole moment, then the dipole will be independent of the origin. So it doesn't matter how you pick your origin, the dipole moment will always be independent of the origin. But the higher moments, the quadrupole, octupole, and so on, are going to be dependent upon the origin. And if you continue with this, then if you had no charge, you were neutral, and you were nonpolar, so you had no dipole moment, and your lowest non-zero moment happened to be an electric quadrupole, then the quadrupole would be independent of origin, and octupole, hexadecapole, all the higher moments would depend upon origin. So this is true, generally as you continue on with the moments. So this is just a helpful little thing to keep in mind as you're looking at the moment expansion for a molecule. Okay, so next we've learned how to calculate the electric field that's generated by a molecule. So now what we're going to do is look at the molecule in an electric field and how the forces that might be acting on it. So we've learned then that the electric field, in chapter 1, we learned that the electric field is a conservative force. And so because it's a conservative force, it can be written as the negative gradient of the potential energy function. And we know that for some point charge in a scalar potential, that the potential energy is just the point charge times this electrostatic scalar potential. So at this point, I just want to mention that you want to be really careful, because some textbooks use the symbol capital V for the electrostatic scalar potential, and the symbol U, for example, for the potential energy. So let's make sure that we're clear on what's what in terms of our definitions. So when I use this phi term here, it's going to be used to represent the electrostatic scalar potential, and capital V will be the energy, the potential energy scalar, this potential energy function. So let's be careful not to confuse these guys. So this is a potential energy, this is the electrostatic scalar potential, and they're related to each other. So if you want to know the potential energy for a charge in a scalar potential field, it's just that charge times this guy. You can think of this guy as just the potential energy per unit charge in a sense. Okay, now we've already learned that some molecule, which has some charge density, I'm going to call this molecule 1, so I'm going to say its charge density is rho 1, will generate an electric field or scalar potential, electroscalar potential here at this point in space, and we know how to calculate this guy in terms of the moments, the charge, the dipole moment, and the quadrupole moment of this molecule. But what we're interested in now is what does this molecule do in the presence of this electric field? Now, it could be the electric field that's generated by this molecule, or this could be a molecule that's just bathed in an electric field from, say, maybe it's in between two capacitor plates, and then there's a voltage on the capacitor plates, and the molecule is in the externally generated electric field. Or it could be generated by nearby molecules. It doesn't really matter. At this point, we're interested in how this guy behaves in some scalar potential. In this case, it's generated by a nearby molecule. So we're going to describe then the nearby molecule, molecule 2, is having its charge density. We'll call that rho 2. And from the potential energy of molecule 2, we can say that if this guy's in an electric field, just like the analogy here, instead of the test charge, a point charge, we're going to use the charge density. So this guy's charge density in a scalar potential, so in this case it's the scalar potential of this molecule, but it could be some external electric field that's generating this, then this volume integral will give us the potential energy that's being experienced by that molecule. Okay? And once you know the potential energy, then we know that for a conservative force, we can calculate the force acting on this molecule. Now in this case, this example I'm giving you, this potential scalar electrostatic potential is coming from molecule 1. So this potential energy that this guy, potential energy field that this guy is in is coming from molecule 1. And so the force between them is going to be calculated by taking the negative gradient of this expression. All right, so let's then look further then at this electric behavior of this guy in an electric field or a scalar potential. So if we moved ourselves into the frame of molecule 2, so let's think about it, this problem from you're sitting inside here in molecule 2 and you're in some electrostatic potential or an electric field. And we're going to write down that the scalar potential that you're in can be described as a series expansion. So we're going to do another Taylor series expansion about an origin in molecule 2, the one that we're interested in, and we're going to write it out like this. So there's the leading term, the scalar potential in the middle of the origin of the molecule 2, and then we're going to write out these additional terms in our Taylor series expansion. So this is to say that it originated from molecule 1, but let's just say it's just some general electric field that the molecule's in. So we'll drop the 1 subscript here and just say that our molecule now is sitting, our molecule 2 is sitting in some scalar potential that can be written like this. So I've taken the definition of the electric field, which is the gradient of the scalar potential, and I've used that here. So the negative E is the negative of this guy, which is negative, the gradient of this guy is the E, so we have the negative sign there. And then this guy becomes the second derivative of the electric field. And so we get this expansion in terms of the scalar potential, the electric field vector at the origin, and then the gradient electric field at the origin. If we take this expression here and we substitute it back into our expression for the potential energy for our molecule 2, then we'll get this expression here, where now we'll find that we can redefine the potential energy in terms of the multiple moments of molecule 2. So here we see the monopole moment of the molecule, the dipole moment, electric dipole moment, electric quadrupole moment, and how we form the potential energy expression for this molecule in the electric field is we need the charge times the electrostatic scalar potential, the dipole moment times the electric vector, the quadrupole moment times the derivative of the electric field vector, and so on. Okay. So this is our expression for the potential energy of a molecule in an electric field. And we're going to describe it entirely in terms of its moments, its charge, its dipole moment, its quadrupole moment, and so on. So the first term is the interaction of the monopole moment with the scalar potential. The second term is the dipole moment interacting with the electric field vector. The third term is the quadrupole moment interacting with the electric field gradient. Now, one of the things we've done in this picture, this derivation, is we assume that the molecule is a rigid body. So in the sense that we know that the masses are all fixed relative to each other. That's our rigid body assumption. So we're assuming that the charges which are attached to these masses are all rigid too. But that's probably not the case. So we know that if you put an atom in or a molecule in an electric field, there might be some rearranging. And if that happens, then these moments are going to change. Now the monopole moment is not going to change, but the other moments may change. So what we know is that the electric field would pull the electrons one direction and the positively charged nuclei the other direction. And if it's a really strong electric field, it could actually pull the electrons off the molecule. That's a very, very strong electric field. But at lower electric field strengths, it will pull them out, but then there'll be some balance of attractive forces that will hold them together. So the molecule will change shape a little bit, but it will still be held together. And that will affect all the moments other than the monopole. Since the molecule hasn't lost any charge and there's no ionization there, then the total charge will stay the same, but the dipole moment, the quadrupole moment, all of those guys will have changed because of this stretching or distortion of the molecule in the electric field. So the way we're going to model that is we're going to say that the dipole moment of the molecule is going to be given by the permanent dipole moment in the absence of electric field, plus some induced dipole moment by being in the presence of an electric field. And this can be written out as the permanent dipole moment vector plus a quantity called the polarizability, how flexible is the molecule in an electric field, in a sense. Polarizability times the electric field vector. This polarizability is a second-rank tensor. So this is a tensor quantity. It's a matrix that you multiply times the electric field vector to get the induced dipole moment vector that adds to the permanent dipole moment vector. So this is essentially then going to be the derivatives of the induced dipole moment vector, the rate of change of the x component with the rate of change of the electric field vector along x, the rate of change of x with the electric field vector along y, and then x along z. And you can see you get a 3x3 matrix, or written in this form here with these alpha subscripts here is the polarizability tensor for a molecule. And this has units of meters Coulomb squared over newtons here. So this gives the direction and magnitude of the induced dipole moment that a molecule will get in an electric field. And it may not be along the direction of the electric field. So if electric field is pointing along this way, the induced dipole moment may not necessarily be along the direction of the electric field. That's why this quantity is a tensor quantity. The electric field could be pointing along this way, and the induced dipole moment could be pointing along some other direction. So we need this tensor quantity to get the orientation of the induced dipole moment vector given the direction of the electric field vector. Okay. Now, the trace of this guy, turns out that the traces of a matrix is the sum of the diagonal elements. So anytime you see, this is generally true, anytime you see the trace of a matrix is just taking the diagonal elements and just adding them up. And that trace turns out to be independent of which coordinate system that you've used to calculate this quantity. So later we'll learn about calculating polarizability tensors, and you're going to have to make some, just like in the moment of inertia case, you're going to have to make some coordinate choice, and it turns out that this trace is independent of your coordinate frame orientation. And when we're looking at these guys in measurements or calculations, one of the things we're going to be interested in is something called the average or the isotropic polarizability, which is 1/3 of this trace. So 1/3 of the trace is a scalar quantity called the isotropic polarizability. This is the quantity that you observed if you're looking at a molecule in a fluid phase, a gas phase or a liquid phase, where the molecule's tumbling. And so even though there's all this orientation dependence here, the average of that tensor works out to be this isotropic value, the scalar value, and that's the value you would observe in a fluid phase. So this is the value that is sort of present when you average over all orientations with respect to the electric field that you're in. Now, to calculate the potential energy in this case, so we talked about calculating potential energy when we had a fixed electric dipole moment. Now, if we're going to have a possibility of an induced dipole moment, we need to calculate the potential energy, and we're going to use this expression here. So this is the energy of a dipole moment in an electric field, and you have to integrate it from 0 up to the electric field that the molecule is sitting in. So if the molecule is in 0 field, then there's no induced electric dipole moment, there's no potential energy associated with that. But if you turn on the electric field, then the molecule will get an induced dipole, and the potential energy of that induced dipole is going to be calculated by this integral. So if I take our expression for the dipole, which is the permanent plus the induced part, and plug it into this expression, I see that the total potential energy expression is going to be the permanent dipole part, which we had before, and now we get this term here, which involves the tensor alpha and the electric field that it's in with this 1/2 multiplication here. So it shows up as E dot alpha dot E. So this is the permanent dipole term, and then this is the potential energy associated with the induced dipole. All right. Now, in work with atoms and molecules, it's a little bit more convenient to redefine another quantity called the polarizability volume, which has units of volume. And it's just taking this alpha quantity and divided by 4 pi epsilon, and that gives you a quantity that's in units of volume. And this is convenient because this quantity tends to be comparable to the volume of the atom or the molecule. So if you look at the volume of the atom or molecule, you can get a good idea of how polarizable it is. A really small atom is not going to be polarizable, but a really large atom is going to be more polarizable and will have a larger induced dipole moment. So here's a periodic table of atomic polarizabilities. So these are the average electric dipole polarizabilities for the ground states, and these are in units of angstroms. So instead of masses of the elements, I placed in this table the polarizability in units of cubic angstroms. And so you can see, as you might expect then, for hydrogen, a very small atom, it doesn't have a very high polarizability, but as you go down the periodic table, you see that they become more and more polarizable. We also know that the trends with radii in the periodic table is that the molecules start out large on this side and they get smaller as you move over. So you can see that the polarizabilities are small on this side, but they get larger as you move from the right to the left. And that, again, just correlated to the size of the atom or the size of the molecule. The polarizability volume is sort of roughly close to that. So that gives you an idea how polarizable a molecule or atom will be, and how much of an induced dipole moment you might expect in an electric field. Okay, so that's it for this video. And then in the next video, we'll look at intermolecular forces between molecules.